Hi all, welcome to lecture number 8. Sorry that I couldn't be there to deliver this, well, not in person, but at least live. We're going to go through one more example of Sturm-Liouville theory, with some perturbation work mixed in. Perturbation asymptotics is a very useful tool in applied math. I think it's worth our while to spend some time to understand it. So I'm going to consider our heated rod example with the area constant, the thermal conductivity will be constant, the density will be constant, and of course I've scaled things in the resulting problem, but C of X, that's the thermal capacity. This will be slowly varying down the length of the rod. And I've scaled things so that I'm in the interval 0 to 1. And I'm going to have C of X being 1 plus 0.01 times X. So it's almost the uniform materials leading to the standard heat equation, scaled heat equation we've had before, except for this term. And now you know I'm probably going to call this epsilon of X, and I won't just solve this problem. I'll solve a family of problems involving epsilon, but approximately, leaving out terms of size epsilon squared. So the resulting equation is this. Let me put in the epsilon instead of the 0.01. And let's, I've kept everything easy except this one slowly varying term. Let's continue to do that and take the simplest boundary conditions, the Dirichlet ones that we started with. Homogeneous Dirichlet boundary conditions. So we're led naturally to the Sturm-Liouville problem. Defined to be 1 over 1 plus epsilon x times this second derivative. And we're looking for eigenvalues. This will give us a series solution for the steady state problem and the time-dependent problem with initial conditions and the time-dependent problem with interior forcing terms with the Duhamel's principle. So where we're kind of interested in the eigenvalues and eigenfunctions that come out of this. And remember, certainly in terms of the time-dependent problem, the thing we're most interested in is the least negative eigenvalue. So let's suppose that we are most interested in lambda 1 of this problem and its corresponding eigenfunction. And we expect that lambda 1 will be close to the epsilon equals 0 case, and the eigenfunction will be close to the first term in the regular sine series. Okay, well, there's a couple of ways that you could go about this. In fact, there's some special functions that solve exactly this kind of differential equation after some change of variables. They're called Airy functions, not to indicate that they aren't serious, but it's some mathematician, Airy, I believe. And in fact, 100 years ago, a lot of applied mathematics was all about understanding the properties of special functions that arose as solutions of differential equations. But luckily, we have another option, which is to look at a perturbation technique, right? So we're going to say, we are going to look for an eigenfunction that looks like sine pi x. Plus something, and of course this is going to be an approximation because we're leaving out the epsilon squared terms over here. And the lambda is going to be minus pi squared plus beta times epsilon. And also approximation because there would be some order epsilon squared terms here. In the notes, it goes back basically to the implicit differentiation approach to these problems, but things are just a little bit faster if we do this technique that I talked about last lecture, which is you just take these forms, you put them in the differential equation, you look at the order 1 terms to make sure that you really are starting with an eigenvalue, an eigenfunction. And then you look at the order epsilon terms to figure out the equations that these things satisfy. There's some interesting things that happen in this particular case. So let's put those in, okay? So if I put those in, I'm going to get, here I am taking the second derivatives of this thing. I'm going to get minus pi squared sine squared sine pi x. Every time I take a derivative, I get a factor of pi. I go to cosine and then back to sine with the sign change. I'm going to get epsilon v double prime. And then some order epsilon squared terms that I'm not going to care about. And then over here, let's remember that this is minus pi squared plus epsilon beta. And this is sine pi x plus epsilon v. So there's a whole bunch of squared terms, but if I'm only looking for constants, the only one I'm going to get is, I'm going to get the minus pi squared from the lambda, I'm going to get the 1, and I'm going to get the sine pi x. That's when we look at order 1 terms, those are the things that are going to cancel out. But now I'm going to get 2 other terms. Let's see if I can get those right. I'm going to get the beta, epsilon beta, and then I've got to have the 1, and then I've got to have the sine pi x. Okay, and then I'm going to have the minus pi squared. Now I'm going to take the x and the sine pi x. Okay, and if we had to do the epsilon squared terms, there would be a bunch of other stuff that would come from that. Okay, so this is the problem that we've made progress on. We're looking at this, and now we're going to look at the terms one by one in terms of the order. And if I look at terms with no epsilon in them, this doesn't tell us anything. It does tell us that the solution that we're linearizing around was actually a solution, right? So that's good. And then more interestingly, let's look at this one. I'm going to have, okay, I messed up here somewhere. I've got 3 terms, but I don't have the 3 correct terms. Okay, let's go back. I've got the minus pi squared x sine pi x. I've got the, oh, and there was an epsilon here. There's an oh, okay, yeah. Yeah, I had 3 terms. I've only got 2 epsilon terms here. There's one more epsilon term that is with the v. So there would be a minus epsilon pi squared v term here. So when I look at the order epsilon terms, I'm going to get v double prime plus pi squared v. And then I've got 2 other terms here on the other side. I've got the minus pi squared x sine pi x plus beta sine pi x. So this is the problem I got for v. Now, interestingly, somehow this problem has to tell me v and beta, which seems like it's a little bit tricky. There's a little bit of a trick to this one, which I'll show you. First of all, we got to get the boundary conditions, though, right? I want whatever comes out of this to satisfy these boundary conditions also with terms epsilon. These terms satisfy the boundary conditions already, so there's no correction. So I've got to have v of 0 and v of 1 is equal to 0. Now, on your assignment, there is a question where you're invited to think about this a little bit more deeply and understand how you could work out what beta was without doing all the work I'm going to show you. But at least in a straightforward way, this is just a standard differential equation where I can solve with the method of undetermined coefficients. I've got a homogeneous part. I've got a particular part. And the only thing that's interesting is this is a resonant case. Sine pi x is already a homogeneous solution. So if I have something like sine pi x here, I've got to have x sine pi x, x cos pi x. And because I've got x sine pi x, I've got to add in a whole bunch of stuff. So resonant method of undetermined coefficients. And remember, these coefficients are different. These are coefficients I'll pick in order to match the, to get the particular solution of this. And the A and the B are coefficients I'll match afterwards to get the right boundary conditions. Okay, so you put this in, you match coefficients to work out the method of undetermined coefficients. Okay, and I'll just say some algebra gives the method of undetermined coefficients. And then if I'm going to match the boundary conditions afterwards, I've got v of 0 is 0. That tells me that b has to be 0. And if I look at v of 1 is 0, that tells me that d plus f is 0. Okay, and if I look back at what those things are, that tells me that minus beta over 2 pi plus pi over 4 is equal to 0. This tells me that beta is pi squared over 2. Okay, so this was the perturbation term from the eigenvalue, right? So now I know that lambda 1 as a function of epsilon, it's approximately, let's write approximately, equal to minus pi squared plus pi squared over 2 times epsilon. And of course, the interesting thing is, maybe the most important thing is, if you have a term like the epsilon term we put in, and it's positive, right? That will slow down the evolution of the temperature in your rod slightly, right? But at least you know the sign of the change from this, and in fact, you know a good approximation of it from this term. Okay, so we got beta, and like I say in the notes or in the assignment number 3, you are expected to look at this a little bit more closely and to have worked out how you could work out that beta in an easier way for a general case. Okay, what about V? There's a little bit of a tricky thing for V because I don't know if you noticed, I worked out that this B was 0. But I never worked out what A was. I worked out what all these little letters were with the method of undetermined coefficients, but A is not determined in this thing. So if you wanted to know the shape change of the dominant eigenfunction, then you would get that phi of x was sine pi x plus epsilon times v of x. But I still haven't really told you why this thing is not determined. And in fact, it is okay to set A equals 0. Now that seems like a bold statement. Well, okay. The reason is A just changes the particular eigenfunction that you picked to start with. Remember, sine pi x is an eigenfunction, but any multiple of it is also an eigenfunction. So this is really a redundant term. You're just changing the size of the eigenfunction that you start with. And if you think that you're changing this by an amount that is of size epsilon, then you're only going to affect later terms that are of size epsilon squared, right? So it's consistent to set A equals 0. This is a bit of a subtlety, and I know there would probably be student questions at this point in the lecture. So save those questions for next Tuesday, and I'll be happy to answer them. If reading the notes on this lecture doesn't help. Okay, so that wrapped up the Sturm-Liouville theory that we talked about before. And now we're going to go on to higher dimensional problems. And when I talk about higher dimensional problems, I'm talking about higher spatial dimension. Right? Because time is time. There's only one that we know of, unless you watch science fiction. But space, we've got this one-dimensional rod. Let's look at how things would look like in 2 and 3 dimensions. Okay, so let's look at a 2D problem. I'm going to have a thin plate with some shape, right? And so I'm going to have my temperature, U of X and Y and T. You can derive a heat equation, a scaled heat equation for this problem as well, with UT is UXX plus UYY plus F of X, Y, and T. And this thing here, this thing is called the Laplacian. Mathematicians write this as the Laplacian of U this way. There's also from physics and engineering, it's often grad squared U is written this way because it's the divergence of the gradient of U. Okay, but I'm a mathematician, I guess, so this is the form that I'll use. It's an initial boundary value problem, so you have to give boundary conditions. Okay, so I'm going to give the simplest ones here, but there's the range of boundary conditions that we talked about in the 1D case. You can have them here, but I'm just going to have homogeneous boundary conditions all the way around, right? So U is 0 all the way around. I can have a 3D object. Okay, I'm not good at 3D drawing. Okay, here we go. All right, okay. Here I'm going to have U as a function of X, Y, Z, and T. Often you would just write it as a vector X. And the heat equation in that setting is UT is Laplacian U plus F of vector X and T, right? And here this is UXX plus UYY plus UZZ. And of course you could imagine problems that were not constant coefficient and not isotropic, so that the thermal conductivity is better in some directions than others. And you end up with all kinds of interesting variable coefficient problems that way. Again, I'm going to have to give boundary conditions. I'll give the homogeneous Dirichlet boundary conditions all the way around as well. Okay, so those problems are interesting. And just like in 1D, right, we can get series solutions for these problems, right? Let me give some initial conditions. I can get series solutions for those from eigenvalues. So they would be solving Laplacian phi is lambda phi with phi equals 0. These will give eigen functions leading to series solutions. Now, of course, as you can imagine, that's a computational problem, right? For general shapes, we're going to look at some specifics of how all of this works in some simple domains, a square and a sphere and a circle, right? Okay, because those are ones where we can really see how this all works in a concrete way with algebra that is doable. But before I get to that, it's the same in 2D and 3D. So let me just talk about the 2D case. We can suppose that the forcing term here is not time dependent. Right, and then you expect, right, because you've got all of these decay rates and these problems, right? All the information from the initial conditions is transient. So you expect that as time goes to infinity, I'm going to have a steady state. And of course, it will solve Laplacian U. Oh, okay, now I've got, unfortunately, the way I've set it up, it's going to be minus F in this case, okay, in those domains. So remember, we like drawing pictures, right? And so I'm really going to have two problems, right? I'm going to have Laplacian U is minus F with U equals 0. This is what's known as the Poisson problem. Right, and this one will have a series solution, right? From the eigenvalues, the eigenanalysis. And then I'm going to have a Laplace problem. With, this is, say I've got my boundary parameterized by a parameter S. I'll have the data. Remember, I can separate out these two problems. If they were together at the beginning with F and G both, I can just separate them out. And this one, just like the time-dependent boundary conditions, which I'm for the 1D heat equation, which I'm leaving for the future, this one needs other techniques. So the boundary, the series solutions that we're going to talk about today aren't going to apply to this particular problem. Okay, so let's pick an example. A square. And I want to solve the eigenvalue problem here with homogeneous Dirichlet conditions all the way around. Okay, and so it takes a couple of steps in the notes, but I think you've seen this before, and even if you haven't, I bet that it's not so difficult to understand that I'm going to have an infinite set of eigenfunctions, and they're going to be the sine series in X and the sine series in Y. So I'm going to have sine m pi X, sine m pi Y. And the eigenvalues will be minus n squared plus m squared pi squared. Okay, so you can check these work. Right, if I take, they satisfy all the boundary conditions. If I take two x derivatives and add two y derivatives, then I get exactly this relationship. Okay. Now, I don't want to to tell you things over and over again if you've already got it. But I do want to tell you things over and over again if you haven't got it yet. So I'm going to say, why did we do this? Because this gives us series solutions for 3 problems. And let me write out the 3 problems that it'll do. So it's going to give us the series solution for Laplacian phi is, okay, I'm going to change the sign so that it's just f, not minus f. I hope that's okay, right? I'm going to be able to get a series solution for that. And I'll be able to get series solutions for 2 other problems. Same boundary conditions. This is going to be du, oh, okay, phi was for the eigenfunction. Let's go back to u for the problem. Sorry, it's all right, it's all right. It's almost like you're getting a live lecture. I mean, I could video edit it all, but then you'd lose the spontaneity of my my mistakes. Okay, so I got the same thing for the He equation with initial conditions u0 of x and y. And I've got the same problem, ut is Laplacian u plus f with 0 initial conditions. And I haven't written it, but it's the same boundary conditions all the way around. So this result here gives us series solutions for all of those. And again, I think maybe you're on it, but just in case you're not, let's write them out. So here's the one for number 1. I'm going to have u is a series. Got a sum over the n's and the m's. I'm going to have a f and m here divided by n squared plus m squared pi squared, and I'll have a minus sign. That's dividing by the eigen value. Where these guys are just the Fourier sine series, the 2D Fourier sine series coefficients. Oh, m pi y, sorry, m pi y. And there's a normalizing factor. Remember, for one sine series integrals, it was 2. So there's a normalizing factor 4 here. Okay, so these guys are orthogonal, right? On the square, the same as before. And you got to have the exact same m and m to get anything non-zero. And you can write these things out as you did. Okay, well, that was problem number 1. Now I have to remind myself what was problem number 2. Oh, that's the initial conditions. So I'm going to have u of x, y, and t. Well, that's going to be, it's going to be a series, n equals 1 to infinity, m equals 1 to infinity. And I'm going to have, now I'm going to have u0 the Fourier coefficients. Okay, it's just the same thing as these ones, but with U0. I'm going to have the shape, spatial shape. And I'll have the exponential e to the minus n squared plus m squared pi squared t. And of course, now you can see the n equals m equals 1 term decays the slowest. Right, okay, so you know the shape of the slowest decaying term in the series. Okay, and then what about the other one with the internal forcing? So now let me get check my notes and make sure I get this right. Well, now I'm going to say, I'm going to break it up into two parts. It's the same series. I'm going to have a coefficient that'll depend on t. We know that these will all be 0 at time 0 because this is the one that I am looking at with the 0 initial conditions. Remember, these two problems are complementary, right? They add up together to solve a more complete problem. So I've got the sine n pi x, sine m pi y. And now I'm going to have the FNM. These Fourier coefficients are going to depend on time, right? Because my f depends on time. So the forcing at every time gets a double sine series representation. And with that, this is just Duhamel's principle. I get the integral from 0 to t right? So I've just divided up these each Fourier term, each Fourier sine term, I've divided up into 1D problems that I can solve exactly the same way that I've solved before. So it might take a little bit of getting used to, but you know, you see these higher dimensional problems, time dependent, maybe not time dependent, maybe initial conditions, maybe internal forcing, but doing a eigenanalysis of the spatial operator is a key to finding a series solution. Now remember, back from the beginning of the course, series solutions aren't the only interesting thing, right? Because we thought Green's functions were pretty interesting too. That's another way to represent the solution. And we will come back to that for these problems, but in a while. Okay, so we had a 2D shape, which was a square. And of course, you're expecting that the next example is going to be a circle, but actually that gets a little bit more complicated. We got to make new friends. We have to make friends with Bessel functions for the circle. So there's an easier second example. which is heat conduction. In a unit sphere. Assuming radial symmetry. Without radial symmetry, the sphere is not easier. Okay, but we're good, right? So so I'm going to look for solutions U of R and T. Okay, and if you here's my unit sphere. Radius 1. And if you look up, I always used to look these up in the first few pages of my electromagnetism book that I had from an undergraduate, which had the change of coordinates for all kinds of differential operators. But if you look it up online now, if you look at the Laplacian in radial coordinates, it is 1 over r squared, d by dr, r squared du by dr. Okay, luckily, I have worked this out when I didn't have my book handy. You know, I was on a trip somewhere before internet, but luckily we don't have to do that. So now I want to look at the eigen value problem for this one, right? Okay, so I want to look for functions that satisfy this. And of course, I have to give some boundary conditions. I'm assuming that I've got a u equals 0 on the outer boundary. So that's phi of 1 will be 0. It's the unit sphere, right? Now there's a hidden condition. At r equals 0 that we'll discuss coming up. So let's think about the conditions for the 1D case. U double prime is equal to lambda u. Phi double prime is lambda phi, with phi equals 0 at the two ends. Right, I got solutions sine and cosine, and I needed the two conditions to be able to say for the eigenvalues, then there's a one parameter family of solutions. The same thing here, I need a condition that r equals 0. We'll come to it, okay. So, okay, the good news is there's some tricky algebra, but it's written up in books places, okay? So if you want to proceed, you introduce a new variable. That's y is r times phi. Okay. So if I multiply through by r squared, I'm going to now have a d by dr. R squared d, okay, phi is y divided by r. And now I get lambda r times y. Because that gives me the r squared phi, r, and another r gives me the r squared. Okay, good. Okay, so now I'm going to have d by dr r squared, and now I get two terms from this. I get dy by dr over r, and I get minus y over r squared. And then if you keep going, you have some nice simplification. And you end up with a d2y dr squared is lambda times y. There's a couple of other steps in the notes if you want to make sure you follow along. The one boundary condition I have, right, is that phi at 1 is 0. That makes y of 1 equal to 0. Okay. But now we can talk about what the other boundary condition is, right? I've got this phi of r. That's this thing I'm solving. That's y of r divided by r. And now you can see where the other boundary condition is going to come from. Nothing singular should happen with this eigenfunction at r equals 0, right? This is heat conduction in a sphere, right? There's no infinite temperature, stuff happening in here, right? We've got a maximum principle, right, for this problem as well. Since phi at 0 is bounded, I know that y of 0 has to be 0. So this is the hidden condition. We're going to have a hidden condition when we talk about Bessel functions as well. Okay, well, I've seen this problem before, right? Not y and r, but u and x, and I know the solutions of that, right? I've just got the sine series in y. And then the eigenvalues are the usual things. And this phi n of r, that's 1 over r sine n pi r. Now that has a limiting value, right? As r goes to 0, it's finite. Remember I said the Sturm-Liouville theory extended to some cases where those terms weren't strictly positive, but where they could be 0. Well, this is why, right? They worked on that extension is for problems like this. So I'll just do a note. These transformed functions, the yn of r's, they're the sine series. They are orthogonal as usual. But these phi n of r's, that's the 1 over r sine, oh, I've got them up here. But the phi n of r's, these guys are orthogonal in a weighted inner product. That's, if I've got something like this and I want them to look like sines, which I know are orthogonal, then if I've got two of them multiplied together, I've got to multiply by r squared. So this will be 0 if n is not equal to m. Okay, just to go back, why did I know that this r squared was going to show up? Physically, I know it's going to show up. because this is the weight that comes in integrals in polar coordinates, right? That is the r squared dr is the little volume element, if you can think back to Math 101. The other reason I know that it was going to come in is if I look at this expression, I'm going to have this Sturm-Liouville term is equal to lambda r squared times phi. And remember the thing over here, the r squared is the thing that comes in the weight for Sturm-Liouville problems from last lecture. So, I mean, I just worked out the eigen functions and worked out that they had to be orthogonal in this way just by looking at them. But there's two other ways you would have known that this term would have been present in the orthogonality relationship. Okay, so now that I've got the sign series for the sphere with only radial dependence, I can solve series solutions for the Poisson problem, for the heat conduction problem in the sphere with radial dependence. Something I said seemed to have started my phone playing music. That's interesting. I was getting excited there too. What was I talking about? Oh yeah, with this series solution, you can solve the same three problems you solved. We solved before for the square thin plate. We can solve for the radially symmetric sphere. Okay, so now we've got the last thing I'm going to show you. This is the one where the Bessel functions come in. If this was a live class, I would have had a poll, which was, are Bessel functions your friends? You know, exactly the same way, you know, distant relatives, you know, that I asked you about variation of parameters. Okay, so I'm going to have a circular plate. This is going to be in 2D, and it'll be the unit circle. And I want to solve eigenvalues of this with homogeneous Dirichlet conditions for exactly the same reason as in the last two cases. This gives me series solutions of those three problems. And again, I can look up what the Laplacian is in radial coordinates. And it's 1 over r d by dr, r d phi by dr, plus 1 over r squared d2u d theta squared. Okay, so I want to solve this eigenvalue problem with phi at 1 being 0. Okay, so let's have a look. Well, oh, this is phi. Motivated a little bit differently in the notes. Basically, it's a separation of variables argument. But let's say for sure, I'm expecting periodicity in theta. And so if I've got a periodic function in theta with some derivatives, I want to think Fourier series. Okay, so I want to write Fourier series in theta. And if you haven't seen it before, It's makes the algebra a lot easier in many cases. I'm going to say it's convenient to use the complex form of the Fourier series. The usual form of the Fourier series has the an cos n pi or n theta terms, right? And we're going to have cos and sine, and we're going to look at e to the I n theta. That's cosine n theta plus I sine theta. Right, and I'm going to have plus and minus terms. And so if you take complex coefficients of these and you take complex conjugate coefficients for the two of those, then you can get any cos n theta term and any sine theta term that you want, and the result will be real. And so using a series of these guys with complex conjugate coefficients is going to give you the same kind of representation as the real form of the series. So I'm just going to say I can write f of x as the sum of a complex Fourier series with the coefficients. These will be complex. Fn and f minus n will be conjugates. Integral from 0 to 2 pi, f of x e to the minus in x dx. And there's a normalizing factor, 1 over 2 pi. In the sine series that I introduced right at the beginning, I wanted my eigenfunctions to be normalized. And so I had 1 over the square root of 2 factor in both of them. You could do a similar thing here and have an alternate form of this where you have a 1 over the square root of 2 pi factor in front of the inverse series as well as the Fourier coefficient expression. And just to make life interesting, you can also see forms of the Fourier series where there's the minus sign and the plus and minus sign are switched. So it doesn't change the mathematics. It just changes the presentation of what you do. So with that in mind, I think that eigenfunctions I'm going to find are going to have split off in terms of Fourier coefficients. So I'm going to look for eigenfunctions of the form phi of r and theta are going to be some function of r and a Fourier term. Okay. And when I say I'm going to look for them, I know I'm going to find them. I'm going to find them all this way. And there's a little bit more justification in the notes. Okay, so now I have to scroll back a little bit. Okay, so here is what I'm going to do. I'm going to take this thing here, and I'm going to put it in to this thing here with this expression, right? Okay, and what you're going to do is there's an e to the I n theta that multiplies everything, right? So that's gonna not show up. And I'm gonna have r times r psi prime, that's d psi dr prime, minus lambda r squared psi. And when I take the two theta derivatives, I get a minus n squared, right? Because I squared is minus 1. And I'm going to move that over here on this side, n squared psi. Again, there's some algebra tricks, which it's lucky for all of us are written up in books, worked out at great length by people who really wanted to understand these problems better. Okay, so no surprise, all the eigenvalues will be negative. And you can show that independently. And so I can write lambda is minus mu squared. And if I do that, I've got r psi prime plus mu squared r squared minus n squared. That's right. Okay, yeah, that's got the sign change, right? Is 0. Okay, now here's an interesting thing where who knew that this would be helpful? Okay, but I'm going to make a change of variables. Remember, I want to figure out what mu is, right? Mu is going to tell me what the eigenvalues are, and I really care about the eigenvalues. So let's do this change of variables, where I'm going to let x is equal to r times mu. But I don't know what mu is yet. I know it's not 0, right, and positive. So I'm changing r from 0 to 1 to x from 0 to mu. Right, and so I'm going to have d psi dr will be mu d psi dx. And I realized that I wrote this down, but I didn't give you the boundary conditions. You've got the real one, right, which is good, right? And then you've also got this hidden one, which was, again, you've got these r going to 0 terms going around. This will be bounded. That's the same kind of hidden condition that we had in the radial case from the previous example. Okay, so there's a few more details in the notes, but if you do this change of variables, then this problem becomes x d by d x d psi by dx plus x squared minus n squared psi is 0. And now if I look at psi when x is mu, right, that's the same thing as psi when r is equal to 1. This has to be 0, and psi at 0 has to be bounded still. Okay, so now you're going, hey, that was a lot of work. This does not look any nicer. This does not look any nicer than it did before, right? But this is where we get to meet a new friend, right? If I'm going to satisfy this equation with this term bounded, okay? Like if it was psi double prime plus, you know, lambda psi was 0, then we would, we'd know we'd have our friends, the sine functions, right? But now we have to make a new friend. So if I satisfy the differential equation and this boundary condition, together, then I know that psi of x is got to be a multiple, right? Right? It's 0, right? So I'm looking for homogeneous solutions. Any solution I find, I can multiply by a constant and get another solution. And this is Jn of x. This is the Bessel function of order n. Now these are like the, you know, like the sine functions. So if there's one Bessel function, there has to be another Bessel function, right? Like the cosine, it's buddied, right? Because this is a second order differential equation. So there's got to be two linearly independent homogeneous solutions. The other one is the other Bessel function, which is unbounded at 0, okay? So they're typically denoted by a capital Y. So if you see a capital Y and you're looking at Bessel functions, it's the wrong Bessel function. You want this one, okay? So let's take a graph of, well, I don't just have one function, right? I've got a whole bunch of functions. Let me do a graph of J0 of x. And remember, I am hoping, right, that okay, where did it go? Oh yeah, here. I am hoping to find some roots of this Bessel function because those will tell me what mu is, and mu will tell me what the eigenvalue is. Okay, so here's J0. Okay, it starts off at 1, I believe. And it's like a sinusoid, but decaying. And okay, remember, it's these roots that we're really interested in because they're going to tell us the mu values. And so this is the first root of the 0th order Bessel function. This is the second root of the 0th order Bessel function. This is the third root of the 0th order Bessel function. And these roots, these are all in tables. Or you can look them up on the internet. And you can also look up J, N, M. So these are the ones that are actually varying in theta. Remember, the 0 is corresponding to the n is equal to 0, which is the Fourier mode e to the 0, which is just the constant in theta. So these n equals 0 ones, they're all for a theta independent eigen functions. But you can also look at the theta dependent eigenfunctions, and they have a bunch of roots, okay? And if you're interested, this first guy, right? This is going to give us the smallest eigenvalue in magnitude. So this is the one we're most interested in. This is the smallest magnitude one. So it's going to be the shape that decays the slowest in the heat equation problem with initial conditions. Okay, well, okay, it's a number, 4048. Right, and like I say, you can look up the other ones. Okay, and if you're interested, this corresponding eigenfunction so now I have to go to phi of r and theta. Well, remember this one was the n equals 0 mode, so constant in theta. Right, okay. The shape is Jn of x. So this is J0 of something. What was x? X is, I know what x is, but like I wanna go back and show it to you. It's, here it is, r times mu, right? So this is so that tells you that, oh, okay, now I'm in trouble. So this is r is x divided by mu, right? So this is J0 of oh, now I'm, okay. This is not in my notes. I'm thinking and talking at the same time at the end of the lecture. Okay, let's get this right. If I've got r, oh yeah, this is just r times mu. Okay, so how do I know that's it? Well, okay, so now I can go, right, if I'm looking in r and I'm going from 0 to 1, right, I'm starting at 1. Here's -1, okay, right, it's symmetric. And once I get to an argument of J0 that is mu, which I'm going to get when r is equal to 1, I'm down to 0. So it's this bump, right, which is not a sine bump. It's a different shape, right, in this radial case. And you could expect that from a sort of physical consideration, that it won't, in the 2D shape won't be the same as the 1D shape, the slowest decaying mode. Okay, and then, well, this is just one eigenfunction, right? I'm going to get a bunch of them, right? I'm going to get a phi n m. And what's that going to be? Well, I'm going to have an e to the I n theta. And then I'm going to have a J0 of r times mu. Now it's going to be the, oh, sorry, Jn. It's going to be the mth root of the the mth root of the nth Bessel function, and this is what we called little j, and these guys you can look up. Right, okay, and once you've got these, there's an orthogonality relationship, which has got an R in it, just like you'd expect, because R is proportional to the area element. And you can solve the same three problems as with series solutions. With these eigenfunctions. Okay, and there's all the details in the notes. Surprising, even though we're not actually physically together, I find it actually quite helpful to have an audience to ask questions when things are going wrong. So I missed that this time. I still hope this lecture and the accompanying notes are useful. Have a look, and any questions you do have about this material, I will be happy to answer at the beginning of the next lecture Tuesday morning. I hope you guys have a good weekend and all the days in between before I see you next week. Okay, I'm going to stop recording.